In our last section in chapter 9, we're going to talk about simple harmonic motion, okay? So we have a list of definitions or terminology that you need to know. Some of this, luckily, is going to be familiar to you. Some of it a little bit new, the rest you've seen before, okay? So simple harmonic motion is vibratory motion that does not lessen with time. What we mean by that is assume no friction, okay? So there's nothing impacting the motion here. There's nothing slowing it down, okay? So we would say assume no friction, okay? And the cool thing about this is sinusoidal curves can be used to model simple harmonic motion. So that means we're going to be looking at sine and cosine waves, okay? Now, to get kind of a better understanding of what is happening here is simple harmonic motion is a repetitive motion, so back and forth or left and right, up or down, just kind of depends. So kind of imagine a spring, and we're going to talk about examples where there's a spring. So imagine you pull a spring down, it's going to go up and down, up and down, up and down. But assume it never slows down with time. Okay. Assume there's no friction on this and it's just going to keep going up and down until we stop it. Okay. So we have this back and forth motion that's going to go through some kind of center position. Okay. And as it goes through this center position, it's going to go up and it's going to go down. Well, the distance from the center position up, the displacement there is going to be the same as it would be for from the center position down. Okay, so this is very much like a sine or cosine wave. Okay, and what we need to understand is that the time for one full oscillation, so like once, like if you start at rest, up, down, back to rest. Okay, the time for that is going to be the same for each oscillation. Okay, so it's going up, down, up, down, up, down. It's not speeding up, it's not slowing down. Okay. So again, it's a repetitive back and forth motion through some center position. The displacement on one side, so like if we're at the center position, we go up, the displacement, the distance from the center position to the highest maximum point is going to be the same as the distance from that center position to the lowest point, okay? And again, the time for one, we'll call it oscillation, or you'll hear some people say one vibration, it's going to be the same. Okay, so that is simple harmonic motion. Now, we talked about this central position. We will frequently call that the rest position. So we'll talk about starting at rest or something like that, or pulling down from rest or pulling up from rest. Okay. But the rest position is that central position. Okay. This is the place where the pendulum, is what we're going to call it, would stop if there was no outside force. Okay, so imagine that spring. You didn't touch it. That is rest. We pull it down, it's no longer at rest. We pull it up, it's no longer at rest. Rest is where it would naturally stop if there was no outside force. Okay, you can also call this the equilibrium, or there's a definition I've seen that calls it the central position. We'll generally call it equilibrium, or rest is what I'm largely going to call it. Now, we talk about displacement, okay? So displacement is the distance from the object's rest position to a place at time t, okay? So imagine, okay, we already know this is going to kind of look like a sine or cosine wave. So imagine this is rest, and we start doing this. And we're like, okay, what is the displacement at time 7 seconds? Well, let's say this is exactly 7 seconds. So how far is this object from rest? What is the displacement? So we could measure the displacement at any given time. Okay. So the displacement is just the distance from rest at any given time. Okay. Maximum distance is going to be the highest it can go or the lowest it can go, depending on which way you're looking. Okay. Now, amplitude, we've talked about amplitude before. Okay. So you may remember we talked about these back in chapter 7. We had like y equals a times cosine of omega t or omega x, let's call it x. And then we also had y equals a times sine of omega x. Do you remember those? Please don't say no. As your trig teacher, I want you to be like, yeah, we totally remember that. Okay. Well, we're going to see that again. Okay. And amplitude was this little critter right here. We said, hey, if we take the absolute value of a, that becomes our amplitude. Okay. So Amplitude, in case you forgot, is the distance from the object's rest position to its point of greatest displacement. Okay, so the from rest to the max displacement in either direction, that is your amplitude. How high can it really go from rest? How low can it really go from rest? Okay, so that's amplitude. That should not be new to you. Okay, period. Now, this we've talked about the period, but we're going to talk about it very specifically for this simple harmonic motion situation. Okay, so the period, it does represent in a regular sine wave or a regular cosine wave, the period represents the distance for one full cycle of sine or cosine. Okay, well, here it means a little bit more. It doesn't just mean the distance to fill in one full sine wave, or not wave, but one full cycle of sine or one full cycle of cosine. What it means here is it's the time to complete one vibration or oscillation. So we're quite literally going to be looking at a unit of time here. Okay, so the period is the time required to complete one vibration or one oscillation. Okay, so again, if this is rest, and let's say we start at rest and we go like this back to rest, how long does it take us to go from rest back to rest? But like go, I guess I didn't really say that well. We go down, back to rest, up, and then back to rest. That's what we're talking about, like one full oscillation. Okay. And then finally, we have the frequency, which might be kind of new for you, but if you stop for just long enough and think about it, it should kind of make sense. The frequency is the number of oscillations per unit of time. So let's really stop for just a moment and think about that. The period is the time required for one full oscillation. Okay, the frequency is how many oscillations occur per unit of time. So let's just pretend. So I'm even going to put pretend here. So pretend that we have that our period is 4 seconds. Okay, that means it's going to take 4 seconds for one full oscillation to occur. Okay, well, then the frequency, which we usually use a lowercase f, is just going to be 1 over 4. It's quite literally going to be the reciprocal of whatever your period is, because we want to know how many oscillations can occur in one unit of time. Well, if one full oscillation takes 4 seconds, then 1/4 of an oscillation occurs per second. Okay, so there's going to be at least a few questions that talk about the period and the frequency here. Okay, so that is the terminology that you for sure need to know. Again, some of this is repeat, some of it's new. Just hang with me. Luckily, we're dealing with these again. We're going to look at them kind of in a different light, but it's basically the same exact functions. Okay. So let's go down here, and I do have a video, so I'm not going to show it in this particular video, but if you want to go to the electronic version of this worksheet, you can watch this video. Another one of the math instructors in the math department made this video kind of showing how this simple harmonic motion really does relate to a sine wave or a cosine wave. Okay, now formulas. We need to know a few things here. So we have our just displacement formulas. That's essentially what we're finding. We're finding some function that represents the displacement d at some number or at some time t. Okay, so we're looking for these. You might see them in function notation, as in you're definitely going to see them in function notation. So you would see something like this. They mean the same thing, so don't be alarmed by the different notation here. All right, so those are the functions we're looking for. We, of course, need to fill in some really important information. We need to fill in A, the amplitude, and omega, which tells us kind of like, is the period being compressed or stretched? So remember, when you're dealing with sine and cosine, the natural period is 2 pi. Omega is either going to stretch it or compress it, depending on the situation, okay? So we've got our displacement formulas or our displacement functions. We already know that amplitude is the absolute value of whatever A is. Okay, and remember that's the maximum displacement from the rest position. And then the period, remember this. This is stuff that we talked about back in chapter 7. We use T, uppercase T, or tau technically to represent the period. And you take the natural period of your sine function and you divide it by omega. So the natural period for sine and cosine is 2 pi. So we just take 2 pi, we divide it by omega. That is our new period. So if the original period of sine or cosine is 2 pi, omega is either going to compress it or stretch it. So it's either going to shrink the distance that sine has to complete a full wave or cosine, or it's going to stretch the distance that sine or cosine has to complete a full cycle. And then we have our frequency here, which we already know is the reciprocal of the period. And then just for fun, real quick, let's remind ourselves of what the sine and cosine waves look like. Okay, so I'm just looking at these for basically one cycle of sine and cosine. So for our first graph, we have y equals cosine x. Remember, it starts technically, if you're looking at like the OG cosine, it starts at 1 and then it goes to the origin, and then it goes down to -1, it goes back to the origin, and then it goes back to +1. In this case, we don't necessarily know what the amplitude is, so we could say this is A and this is -A. So we don't start at rest. Well, we could say we start at rest. We start at up here, not at rest. So like imagine this right here is your equilibrium or your rest position. So let's go ahead and decide that. Let's say this is rest, okay? We could say we pull the object, whatever it is, up, and then we release it, and it would immediately go down and then back up, okay? Now, if we look at y equals negative cosine x, that would be, for the OG cosine wave, we would start at -1, we would go up through the origin, up to +1, back down through the origin, and then down to -1. Well, let's say this is A, this is -A, and let's say again this is rest. So we could say, hey, we have some object, we pull it down, and then we let go, and it's going to immediately swing upwards. It's going to go to its maximum displacement, excuse me. It's going to go back through rest and then back down to its maximum displacement on the lower level, and then it's going to keep doing this over and over and over and over and over and over, okay? Now we have y equals sine x. So you would use a sine function if you're starting at rest, okay? So imagine you have something at its rest position and you like smack it up, okay? So it's going to go up to its maximum displacement, back down to rest, down to its maximum displacement, and then back up to rest, and it's going to keep doing that. So if you're starting at rest, this sine wave or the sine function would make the most sense. Now imagine, again, we start at rest, so we have y equals negative sine x. So we would start at rest, so imagine some object and you smack it down. So it's immediately going to go down, and it's going to go to its maximum displacement down, and then it's going to go up past rest, maximum displacement up, and then back to rest, and then it's going to keep doing that over and over and over and over. So that's kind of what these graphs are going to look like. So be mindful of where you're starting at. If you're not starting at rest, you would use a cosine function. If you're starting at rest, that equilibrium or that central position, you use a sine function. So starting at rest, use sine. Not starting at rest, use cosine. All right, so let's get through this. I decided to only make one video for this worksheet, so it's gonna be a little bit longer. So let's get to it, y'all. All right, first question. Consider the function modeled by d of t, so displacement at some time t, equals sine of pi times t, okay? Where t is the time in seconds. So we are measuring time in seconds here, so keep that in mind. That is going to matter here, okay? So the question here is, how long will it take to complete one oscillation? Well, if we go back up to our terminology, we had one really, really, really important definition called the period. The period is no longer just the distance for a sine to complete one full cycle or for cosine to complete one full cycle. This is now the time required for one complete oscillation, okay? So if we go down here to example 1 part A, it says how long is it going to take to complete one oscillation given this function right here? Well, we need to figure out what the period is, okay? And remember the period, we either, if you're Jillian, use capital T, if you're real fancy, you use tau, okay? But we take the natural period of, in this case, sine, which is 2 pi. We want to divide it by omega. Well, omega is whatever you're multiplying t by in the argument, Okay, so we want to say, okay, well, this is going to be 2 pi divided by omega, which is pi. Well, the pi symbols, the pi's are going to just divide out to become 1. So we're left with 2. Well, what does this mean? This means it takes 2 seconds to complete one oscillation. All right, so that's what that 2 means. Again, it's not necessarily just the distance, okay, to complete one sine wave. It's the time required, okay, because now we're talking about some function in terms of t. It's the time required to complete one oscillation. So then part B says, well, okay, cool. How many oscillations can be completed in 1 second? This right here is asking for the frequency. And we know that if it takes 2 seconds to complete one oscillation, then in just 1 second, 1/2 of an oscillation has been complete. So you can always take your period and just find the reciprocal of it. So we would say 1/2 of an oscillation is completed per second. So please understand how we go about finding the period and the frequency and how they're related to one another. Okay? Now, in example 2, we're going to have 4 different functions and we just want to describe them. Okay? Whoops. Can I fit? Yay, I can fit at least a whole one on my screen at one time. Okay, so example 2 again just says describe each function. And for part A, we have d of t. So we're looking for the displacement at some time t. And we have 5 sine of 3t. Okay, so we want to know the maximum displacement. Now, if we mosey on up a bit to our terminology, we had another definition that kind of made sense. It's something we've seen before. We were talking about the amplitude. And the amplitude is the distance from the object's rest position to its point of greatest displacement. So when we're talking about maximum displacement, we're really just talking about the amplitude here. Okay. And remember, the amplitude is the absolute value of whatever the coefficient, like the multiplier of cosine or sine is. Okay. So when we come down here, we have 5 times sine of 3t. So the maximum displacement is going to be the absolute value of 5, which is just 5. So the maximum displacement is going to be 5 units up or down from rest. All right. Now we have the period. So we've already played around with the period. We did that in the previous example. So remember, the period is always, for sine and cosine, going to be 2 pi divided by omega. And in this case, omega is 3, so it's going to be 2 pi over 3. And remember, we're talking about the time to complete one full oscillation here. That's really what our period is. So let's just assume seconds. So let's assume t equals seconds. So we would say 1 period is complete in 2 pi divided by 3 seconds. Now, if you want to get really technical and ask yourself, well, how many actual seconds is that? Well, 2 times pi divided by 3 is 2.09 seconds, okay? So we're dealing with 2.09 and then several decimal places seconds to complete one oscillation. Now the frequency. All you have to do for the frequency is find the reciprocal of your period. So we would say 3 over 2 pi oscillations completed per second. Okay? So that's pretty easy. Just understand what's going on with the period and the frequency. Okay, now the last 2 questions, really stop and think about them for a second. We want to know, okay, what is the displacement at time equals 0 seconds? So what that's really saying is, where is this object at t equals 0? Okay, now if we get 0, that object is at rest. If we get anything other than 0, that object has been pulled up and is being held there, or it's been pulled down and being held there. It hasn't been released yet, but it's being pulled away from rest, okay? So you can think about this logically, or you can just quite literally plug in t equals 0, okay? Now, if we think about it logically, if we're dealing with sine, We know the sine functions start really here at the origin. So we would say with sine, they start at rest. So if you're dealing with a situation where you're told that this object starts at rest, then you know you're using a sine function. If you have a cosine function, you're not starting at rest. That object has been pulled up or pulled down and being held until time starts and you release it, okay? So you can just sort of think about it logically, or if you're more comfortable, just do the algebra. We could say, okay, well, what is d of 0? Well, d of 0 is, what did we have? 5 times sine of 3t. Let me double check that really quick. Yeah, 3t. So we're going to get sine of 3 times t, which is 0. So 3 times 0. So that's 5 times sine of, well, 0. Okay. And if you can imagine your unit circle, well, we're at 0 radians right here. What point is on your unit circle? It's the point 1, 0. And remember, x is cosine, y is sine. So what is sine of 0? Well, it's 0. So we would get 5 times 0 equals 0. So what this tells me is we're 0 units away from rest. So at time equals 0, we're at rest. So we're at that equilibrium point. Okay? Now, especially be careful on this last one. What is the initial motion? So at time equals 0. So let's say time equals 0 and then you start the clock. Okay? What is the initial motion of our object going to be? Well, we can kind of go back to those little graphs I showed you up here. So at time equals 0, let's say we're here. So we have y equals positive cosine of x. Okay? So we're starting above rest, but then we're immediately going to go down. So the initial motion is down. Okay? We're above rest, but when we let go, it's going to go flying down. Okay? Now let's imagine we have y equals negative cosine of x. Okay? Well, we've basically pulled our object down here below rest. So we've got some object, we've pulled it down below the rest point, and then when time starts, we're going to let go. Well, what's going to happen to that spring or that object? It's going to go flying up. So the initial motion here, well, it's going to be up. Okay? And then think about sine. So imagine you have some object at rest, okay? And then you hit it up. You smack it up, okay? Well, as soon as time starts, it's going to go up. So the initial motion is up, okay? And then and that's y equals positive sine of x. If you have y equals negative sine of x, you have some object at rest, and then imagine you smack it down, okay? So you smack it down, well, it's initially going to go down. So the initial motion is down. So kind of think about where you're at and where you're going. So for y equals cosine x, we're going down initially. Y equals negative cosine x, we would initially go up. Y equals sine of x, positive sine of x, we would initially go up. And then y equals negative sine of x, we would initially go down. So let's think about, whoops. Let's think about what we have here. Well, we had y equals positive sine of x. So our graph is going to do something like this. It's going to go up and then down and then up and then down. So our initial motion is up. Okay, so that is the initial motion. Let's go ahead and look at part B. I want to kind of go through parts B, C, and D a little bit quicker maybe, because again, I'm just going to do one video for this because it was kind of like all one topic. I didn't really know how to split it up. Okay, so for part B, we have y equals negative 2 cosine of 2t. So the first thing we want to know is what is the maximum displacement? Remember, this is secretly asking you for the amplitude. So we would take the absolute value of whatever we're multiplying our cosine or our sine function by. So we want the absolute value of negative 2, which is, don't put a negative, which is a positive 2. All right, so this tells me my maximum displacement is 2 units up or down from rest. So 2 units from that rest or that equilibrium point. Okay, now the period, remember, for the period, we take the natural period of sine or cosine, which is always 2 pi for these two, and then we divide it by omega, where omega is the coefficient. Woo! Oh, I need to scroll up a little bit. where omega is the coefficient of t inside your argument. So we're going to take 2 pi, divide it by 2. Well, the 2's divide out, which leaves me with just pi. So this tells me the period to complete one full, that's the time to complete one full oscillation, is pi seconds. So one full oscillation is completed in 3.14 blah, 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 blah seconds. Okay? Now the frequency. What is the frequency? It is how much of an oscillation is completed per single unit of time. So what we want to know is, okay, if one oscillation is completed in pi seconds, that means 1 over pi oscillations are completed per second. So not quite, or well, yeah, not quite a third of an oscillation is going to be completed in 1 second. Okay? Or maybe, yeah, that's about right. Okay, so then displacement is, okay, how far from rest are we when t is equal to 0? Okay, so the rest point is like that central position. If our function is -2 cosine of 2t, how far away from rest are we right when the time starts? Okay, so you can think about it. Whoops. If we look at our graphs right here, we're dealing with a situation like this. Pretend this is -2. So at time t equals 0, okay, where are we? Well, we're at -2, okay, because we initially have this item or this object that's been pulled down 2 units from rest and it's being held there until time starts and we let go. So the displacement at time t equals 0 is going to be -2. Now, if you let me scroll. Okay. If you want to do the algebra, that's fine. You could say, okay, well, what is d of 0? It's going to be -2 times cosine of 2 times 0. Okay. Well, 2 times 0 is just 0. So we get -2 cosine of 0. And kind of envision our unit circle. Here we're at 0 radians. Okay. Well, what point is on the unit circle? It's the point 1, 0. So what is cosine of 0? Well, it's just 1. So we would get -2 times 1, or -2. So we're 2 units below rest at time t equals 0. So again, we have some object, imagine it's been pulled down 2 units from rest, and we're just sitting there holding on to it, waiting until the ticker starts, and then we can let go and it swings up. Okay? Now, with that said, what is the initial motion? So we're dealing with this situation right here, okay? We have some item on a spring. We've pulled it down 2 units from rest. At t equals 0, we're at 2 units below rest. And then as soon as time starts, we let go, and the initial motion is going to be upwards, okay? So we would say our initial motion is up. All right. Let's look at the last two. I might scrunch my screen out. That's better. Okay, so for part C, we have d of t equals -3 times sine of 1/2 t. Okay, maximum displacement, remember that's just secretly asking for your amplitude. So we want the absolute value of whatever our sine function is being multiplied by. So the absolute value of 3 is 3. So the maximum displacement is 3 units above rest or 3 units below rest. Okay, now the period. We take the natural period of sine, which is 2 pi. We divide it by omega. Omega is whatever we're multiplying t by in our argument. So it's going to be 2 pi divided by 1/2. Okay, so that's really 2 pi times 2 over 1. Remember, if you're dividing by a fraction, the way we deal with that is we multiply by the reciprocal. So this is really 4 pi. And remember, with our period, it's the time needed to complete one oscillation. So it's 4 pi seconds. Now, with that said, if it's 4 pi seconds to complete one oscillation, how much of an oscillation is completed in 1 second? Well, 1 over 4 pi oscillations completed per second. And if you're wondering what 4 pi seconds is, it's 4 times 3.14, so it's going to be a little over 12 seconds. Okay, so one full oscillation is going to take a little more than 12 seconds, so 1/12 of an oscillation-ish is going to be completed in 1 second. Okay, displacement at time 0. So let's think about this. Okay, When we have a sine function, we're starting at rest, okay? So we're dealing with this little critter right here, where our maximum displacement or our amplitude is 3. Okay, so when time is at 0, it hasn't started yet, we're at rest. Okay, we haven't moved. We're exactly at rest. We're 0 units away. Okay, so you can think about that logically, just kind of imagining the graph, or if you want to, d of 0 equals -3 times sine of 1/2 times 0. Okay, well, that's going to be -3 times sine of 0. And hopefully you remember that sine of 0 really is 0. So we just get 0. So we are at rest. Okay, and then finally, the initial motion at rest, we have a -3 on our sine function. So that means we start at rest and then we immediately go down. Okay, so our initial motion would be down. Okay, now the last one is a little bit weird. Okay, so this one is a situation where we are, it's kind of like a vertical shift. So if you're just thinking graphs, like if we're back in section 7.8 and we're talking about our graphs, this is a situation where we have a vertical shift, okay? So like this is the x-axis, this is 6. So we've shifted our graph up, okay? So this is rest. So 6 equals rest, okay? And then we go up or down from there, okay? And then this right here, this 2, that's going to be our maximum displacement. So let me kind of draw this. So this is 6, this is 8, this is 4. So our maximum displacement is still 2 units from rest. So you can go 2 units above rest or 2 units below rest. So what our graph is going to be doing is something like this. Pretend that's perfect, okay? It's a little tragic looking, but pretend it's perfect. Maybe I can do better. So we would do something like, I don't know that that's much better, but that's what's happening here, okay? So our maximum displacement, we still take the coefficient or like what cosine is being multiplied by, and we take the absolute value of that, okay? So our maximum displacement here is 2. Remember, resting is 6, okay? The period is still 2 pi divided by omega. Omega is still the coefficient of t inside the argument. So we get 2 pi divided by pi over 2. Well, if I'm taking 2 pi and I'm dividing it by pi over 2, that's the same as 2 pi times 2 over pi. Okay? So then the pi's divide out, and I'm just left with 4. So that tells me 4 seconds to complete one oscillation. Okay? And if it takes 4 seconds to complete one oscillation, okay, you know what? I drew my cosine function wrong. Please don't be mad at me. It's late. You know how it is when I make these videos. With cosine, we don't start at rest. We start up here. So our graph would do like this. I just realized that I drew sine, not cosine. Okay, so that's what our graph would actually look like. All right, so we know that it's going to take 4 seconds to complete one full oscillation. So that means like one full cycle is going to be this little critter right here. Okay, 4 seconds to complete one oscillation. How much of an oscillation is completed per second? Well, 1/4 of an oscillation per second. Okay. Now, displacement at t equals 0, we'll think about it. Where is this going to be when time is 0? So like time is 0 is like right here. Well, we're going to be way up here at 8, but let's go ahead and do the arithmetic, not the arithmetic, the algebra. So we get d of 0 equals 6 plus 2 times cosine of pi over 2 times 0. So we get 6 plus 2 times cosine of 0. And we already know from the previous, I think it was part B, that cosine of 0 is 1. So we get 6 plus 2 times 1, which is 8. So you can see it from our graph. But now we have like mathematical proof that at time equals 0, we're at 8. So 2 units above rest. Okay? And then the initial motion, If we're here at time equals 0, as soon as time starts, we're going to immediately go down. Okay, so the initial motion would be down. Okay, so hopefully these four examples have helped you understand like the different components of this simple harmonic motion, the functions that we use for this. Okay, in the next two examples, we're going to actually create the functions. Okay, so example 3 says write an equation for the displacement d of an object from its rest position after t seconds. Okay, so for part A, it says suppose that an object is attached to a spring and is pulled down a distance of 5 inches. Okay, so if this is rest, we're taking our object and we're pulling it down 5 units right off the bat. We haven't let go. We're pulling it down 5 units, and then as soon as time starts, we let go and it goes flying up. Okay? Well, remember, if you're starting at rest, you use a sine function. If you're not starting at rest, you use a cosine function. We're definitely not starting at rest. We're taking some object and we're pulling it down 5 units and holding on to it until the ticker starts, okay? So we definitely want to use a cosine function, okay? So we're for sure going to use cosine something, okay? Now, the amplitude. The amplitude is the maximum displacement, okay? So if we pull this down 5 units and then let go, it's going to start at -5, it's going to go up, it's going to go up to +5, back down. All right, so the maximum displacement here is 5 units. But since we're starting down, we need to put a -5 in front of cosine. Now, the hard part, and it's not really that hard, but the hardest part is figuring out omega, okay? So we know that we have this object, it's on a spring, we pull it down 5 units, and then we eventually release it, okay? The time for one oscillation is 3 seconds. So we know our period is 3 seconds. But we also know the formula for our period is 2 pi over omega. Well, if t equals 3 seconds and t equals 2 pi over omega, then 3 equals 2 pi over omega. So we can say 3 equals 2 pi over omega, and then let's just solve for omega. So let's start by multiplying both sides here by omega. On the right, the omegas just divide out. So we would be left with, let me scroll down just a smidge more. So we would be left with 3 omega equals 2 pi. I want to get my omega alone, so I would divide both sides by 3. Well, 3 divided by 3 is 1, which leaves me with just omega by itself. Whoops. So that tells me omega is 2 pi over 3. So what I want to do is I want to plug omega in. And remember, our generic function is going to be y equals a times cosine of omega t. Well, we've got our a, that's our amplitude, or not our amplitude, but it's our maximum displacement. And then omega is going to be multiplied by t inside the argument. So all we have to do is say 2 pi over 3 times t. And this, y'all, is our function, okay? So this is not the hardest thing you're ever going to do, and I'm not intending to test you and make this something miserable. I want you to understand just really the basics, okay? Now, part B, suppose an object attached to a spring is pushed up 4 units or 4 feet, okay? So again, imagine you have some object on a spring and you're lifting it 4 feet above its resting position and you're holding it, holding it, holding it, holding it. Somebody starts the ticker, you let go, okay? So we have, again, if this is rest, we've got our object up here. We're holding on to it until time starts. Time is eventually going to start, and our graph is going to do this. All right, so what is the function? Okay, well, we know we have to be of the form d of t equals a times either sine or cosine. In this case, since we are not starting at rest, we definitely want to use a cosine function. And then we're going to have cosine of omega t. So we have to figure out what A is, and we have to figure out what omega is, okay? Well, from rest, we had some object and we pulled it up +4 units. So that tells me that A is going to be +4. So A is pretty easy. It's the omega that takes a little bit of energy, okay? So go back into the problem and figure out how much time it's going to take to complete one oscillation. Well, we're told the time for one oscillation is pi over 2 seconds. So our period is pi over 2, but our period is also 2 pi over omega. Well, if t equals pi over 2 and t also equals 2 pi over omega, then pi over 2 and 2 pi over omega have to be equal. You have different ways you can solve this. For me, I see a proportion, okay? If I have a fraction equaling another fraction, it's a proportion, and I can just do my cross multiply stuff, all right? So I'm going to say, well, I have pi times omega equals 2 times 2 pi, which is just 4 pi. All right, I want to get my omega alone, so I need to undo the multiplication of pi and omega. So I divide both sides by pi. Pi divided by itself is just 1, which leaves me with omega equals, well, 4 pi divided by pi, the pi's divide out. So I'm just left with 4. Okay? So we would get d of t equals 4 times cosine of 4t. And that's all she wrote. Okay? So I know this is a long video. Kudos for sticking with it. I think the world of y'all. Y'all are great mathematicians. I don't think this is going to be the video that gets you, even though it was a little bit long. Okay? So there you have it. That is simple harmonic motion. This is what I would expect you to know. Understand the period and frequency and how they kind of play off each other, be able to describe all the things we did in example two. So maximum displacement, which is really just amplitude, be able to find the period, the frequency, understand the displacement at time t equals 0. So where are you at before the timer actually starts? And then understand your initial motion. Are you going up? Are you going down? Okay. So there you have it. That's it. Hopefully this wasn't too bad. Definitely let me know if you have any questions. Okay.